This week we're going to be learning about different isotopes of an element and the atomic mass of these isotopes. And some of the questions we're going to need to answer to really understand what an isotope is and why it exists is, where did they come from and why are some of them more abundant than others? Because some students often confuse the words ion and isotope, since they both start with I and they're both talking about atoms with different numbers of particles, I want to just clear it up right now that an ion is something that has a charge, and this is because of a different number of electrons than the number of protons. Okay, so here's an example where this atom here is our normal hydrogen atom, which has one proton in the nucleus and one electron around it in the electron cloud. This is a normal hydrogen atom, and so if it has one proton and one electron, if you subtract those two, you find out what the charge is. So since they're equal, the charge is 0. So a normal hydrogen atom would have a 0 charge. Hydrogen is interesting, and it can gain an electron, which would be shown in this direction. So if it gets a new electron, now it's got 2 floating around its single proton. If you take the number of protons minus the number of electrons, 1 minus 2, you get -1, which means that the charge of this hydrogen atom would be -1, and so we would write H minus, and this is called an anion because it has a negative charge. If our atom lost an electron, we'd go this way. And now you just have the proton with no electrons around it, so it doesn't even have an electron cloud. This has one proton, no electrons, so 1 minus 0 gives you a +1. And so the charge of this atom would be +1, so you write H+. And this is a cation because cations have positive charges. Okay. So what makes it different from an isotope is that ions have different numbers of electrons, but isotopes have different numbers of neutrons. So here, let's look at this definition of an isotope right here. Isotopes have different masses, so some are heavier, some are lighter, because they have different numbers of neutrons. But they're still the same element because they still have the same number of protons. So let's look at these isotope Bohr models here. If you look at carbon on the periodic table, carbon has a mass of 12.01. 12.01, if you round that, you get a mass number of 12. So that means that the most common isotope of carbon is carbon-12. To get a mass of 12, you have to have 6 protons and 6 neutrons. Remember, the atomic number comes from the number of protons, and that identifies the element. So carbon has an atomic number of 6, but it has a mass number of 12 because you can add together the protons and neutrons. So this nucleus basically weighs 12. If you take away these electrons, the nucleus is the most important part for this isotope definition. Okay. Then we come over here. If you count our protons, they're still the same. We still have 6 protons, but now we have an extra neutron. And this extra neutron gives you a higher mass for your nucleus, and this is an isotope of carbon-12. This one is carbon-13 because if you add 6 and 7 together, you get 13. And then you can add even one more neutron, so now you have 8 neutrons, and you get carbon-14, which is shown here. And this is the heaviest of the 3 isotopes. These all technically exist, but depending on the number of neutrons, a nucleus of an isotope could be unstable, which means that it breaks down easily. And this is because it has too many or not enough neutrons, and this causes an atom to become radioactive. So if an atom somehow has too many neutrons or not enough, it will become radioactive. So the stable isotopes of carbon are carbon-12 and carbon-13. These both exist in nature. Carbon-14 is really rare because it is not stable. It can form, but it doesn't stick around for very long because it becomes radioactive. It has too many neutrons for these protons to be able to stick together. So the nucleus actually breaks down, and that's what we call radioactivity. Okay. Nuclear fusion is how we can form any type of element that exists in the universe, and this all happens inside of stars like the sun. So the sun is made out of hydrogen. Hydrogen just has proton and has an electron, and there are neutrons that can collide, and different small atoms can collide with one another, and they can create bigger atoms. And when this happens, we call that nuclear fusion. So here we have a picture of that. Two small atoms colliding to make a big atom. And during nuclear fusion, there's energy that's released, which is part of why the sun is very hot. So nuclei, or more than one nucleus, can collide or crash together and make big nuclei or big atoms. And so this is another picture of that. So let's say here we have a hydrogen atom with a mass of 2, and here's another hydrogen atom with a mass of 3. They can crash into each other, and now we can create the element helium over here. It's got 2 protons and 2 neutrons. And there's an extra neutron that broke off in this process, but energy is also released. So here's our bigger atom that was made from 2 smaller atoms. So it also has 2 protons now. It still has 2 neutrons. So this is how all of the different elements form in the universe. We can just keep making bigger and bigger atoms. So knowing how abundant or how many of an atom there are in the universe comes from the stability of the different isotopes. So if an isotope is more stable, it's going to be more common because it sticks around for longer without breaking down. Ones that are unstable will break down easily in a radioactive way. So that's what I'm trying to get the point across right here in this sentence. So to show you what I mean by abundance, let's look at carbon again. The normal, most common isotope of carbon is carbon-12, and it accounts for almost 100% of the atoms out there. Really more like 99%. And carbon-13, so yeah, this is a bad, it should say 99%. Carbon-13 with the extra neutron is about 1% of the carbon out there. So this picture is like if I took a chunk of pencil lead or a chunk of diamond or any other carbon-based substance, and I was to count how many of them are carbon-12 and how many of them are carbon-13, we might have a few carbon-13s floating around, but if there are 4 carbon-13s, then there should be 396 carbon-12s surrounding it because the carbon-13 only account for 1%. So that's what we mean by abundance. So when you look at this, if I took the mass of this whole thing and then divided it by 400 atoms, I should get a number close to the mass of just a regular carbon atom, carbon-12, because it's way more of the atoms that are in this sample are carbon-12, and that's the same thing for our average atomic mass on the periodic table, and we're going to talk about that in the next slide. So whenever you take a typical average, you add up the different parts, and then you divide by how many there are. So let's say this is 4 plus 4 plus 4 plus 4, and since there are 4 different things, you divide by 4, you end up with the average of 4. Well, maybe 4 is a bad example. Okay, 3 plus 3 plus 3 plus 3, that gives you 12. So if you took the number 12 and you wanted to know what the average mass of each part was, you would just divide by how many there are. You can divide by 4. So the average you get would be 3. In a weighted average, however, some parts might be more common, like here carbon-12 is more common than carbon-13. I just kind of took this picture and I'm trying to apply it to what we're talking about. The weighted average takes into account the fact that there are way more carbon-12 atoms. And so the average value shifts closer to the side with carbon-12 because there's a lot more of them. So that means if For our carbon isotopes, the average atomic mass of the element carbon, which includes carbon-12 and carbon-13, should be a lot closer to the mass of carbon-12, which is true. If you look at the periodic table again, I'll remind you, carbon has an average atomic mass of 12.01. 12.01 is very close to 12. It's not very close to 13, and that's because 99% of the carbon out there is carbon-12. So in the next video, I'm going to give you a few example problems of calculating average atomic mass, which is really important for you guys to be able to do. And I kind of give you some steps, so make sure you look at that video.